Hello everyone, I am Bradley Sward, Associate Professor of Computer and Information Science at the College of DuPage in Glen Ellen, Illinois. And this video today is going to just look over a slightly more complicated truth table than normal. We're going to look at 3 variables and just checking to see what we see when we go through these examples. So this is what I have here. We're going to compare these 2 items here, and this one looks foreboding, but we'll get there. And so we have C or A and not B versus not quantity, not C, and not A or B. And so what we're going to try to see here is basically we have a system here where we have 3 inputs, right? We have an A, we have a B, and we have a C. And some of them are coming in positive and some of them are coming in negative. And we just have to figure out, my goal here is to check to see what happens with this statement versus what happens with this statement. Like, let's just compare the 2. Let's figure out, let's get the 2 going and get the 2 figured out and get them resolved for their logical, their logical conclusions. And then we can compare what's going on. So that's where I'm going with this thing. And so, like I was saying before, since we have 3 inputs here, an A, a B, and a C, there's no way to know if they're true or false. There's none of them are coming in like always. They wouldn't be variables anymore. They would be constants, like true or false, like a T or an F coming in. Be like, well, this is always true. There's always voltage coming in, or in this case, there's never voltage coming in, or something like that. So we have what we have here. So let me just set up, because of that, we have 8 different possible ways this thing can be set up. And I'm going to be using zeros and ones instead of trues and falses for this. And so if you want to think of this, you could just start counting binarily. Whoops, I did not account for this. Let me change the font on this very quickly. And you can see, so if A is false and B is false and C is false, and then just start working your way up. Just type it up like it's binary. And you'll get all 8 possible, 8 possibilities. And so you get basically binary 0 to binary 7. Binary 0, every A is off, B is off, and C is off. Binary, and like this binary 7 is A is on, B is on, C is on. And so now we can see this. We have our A, we have our B, we have our C. We have our 8 possible inputs that come into this system. And it's the same deal for this versus the nots, right? I have to steal that symbol. I do not have that symbol. What ASCII, or not ASCII, what Unicode character is that? I do not know. And so, of course, if you're going to knot this thing up, it's the complete opposite. So it kind of is counting down now, right? Instead of counting up. If you want to just think of it, so if you just start working your way down from 7 to 0 instead of everything else, it all just comes out like you might expect it. So let's see. So there I go. So, and of course, every not A needs to be the opposite of every A. So 4 zeros, 4 ones, 4 ones, 4 zeros, and so basically, everything has to add up to exactly 1 as I go through. 0, 1, 0, 1, 0, 1, 1, 0, 1, 0. Okay, good. So I have basically my, these are my inputs, and now I'm going to start working my way toward these these statements and then find their conclusions. And so now, just to borrow this, I don't know why the character actually changes when I go to edit, but you can see now what happens if I do C or A. So let's see, this one would be a false. I guess for the moment I could change the colors on these just to kind of get a feel for it. So we can change these to yellows for a brief moment here. I'm gonna OR them together. So 0, that's a 1. So just basically add them together, and if there's a 1 in either one of them, then I have myself a 1 at the end of the day. So that's the first part. You can only do this step by step. You really, mathematically, logically, you're supposed to just take everything one tiny step at a time, because if you jump steps, you're not proving anything. You're just jumping through steps and jumping through and just trying to, quick change everything and just say, trust me. Like math, there's very little in math that goes off of just trust me. Maybe there's nothing in math that goes off just trust what I have to say. So now I can finish this guy up once and for all here. Oops, I didn't mean to borrow this. Okay, let me go in there and move this over a little bit. And now you can see, now what I can do is take whatever I just did. Let me get rid of the font here just to show you here. So now what I'm doing is I'm taking this column that I just did, and I'm going to AND that with not be. So in this case, I'm looking at this. They both have to be 1s for this thing to come through and be a 1. So it looks like I have 3 things that come out of this, right? So I have, so taking this, this is a 0, that's a 1, 0, a 0, 1, 1, 0, 0. So this seems to be, at least right now, we'll have to do a little more work, but at the moment, I feel like this is the answer to this problem right here. Let me use this color just for that. Okay, so I have my answer to the first part. And now we have to check, let's do the other here. Let's do this one here to see what we get. And so now I'm going to start with the first part of this, which is this guy. And you can just continue on. There's nothing stopping you from doing this. Just now I'm going to, let me take these colors out here. Let me just undo this, no fill. And so now what I'm doing is I'm taking not C and I'm using it, and I'm going to do an AND with not A. Now these are the 2 columns. So now I have to see, again, because it's an AND, I have to see a 1 in both spots, right? So far, that's good. Because all of these are 0 because these are zeros. And then this is a 0, that's a 0. So yep, two of these things are that. Okay, at least we're good for the moment. So let me borrow. Now we can say I want this statement here, which is, let me just put some parentheses because I've already done the first part of that. And let me just put this around because this is getting complicated when it comes to seeing everything. Go. Forgive me, let me just advance this a little bit more here. Okay, so now we have ourselves this. And now what I'm trying to accomplish is get rid of this guy. What I'm going to do is take this column, make that yellow, and I'm going to now OR that with just straight up B, right? These guys right here. So I've already done this part, and now let's OR these together. So if you see a 1, throw a 1 in there. And if you don't, 0, I see 1, I see a 1. I don't see any more zeros here, but I see a 1 here, and I don't see 1 there, I don't see 1 there, I see 1 here, I see 1 here. Okay, so now I have this whole thing inside the parentheses is complete. And now, just to finish the deal here, now the final step is to not this guy. Okay? So then just to finish everything off, what I can talk about here is now I want to take this column, and I just want to knot it, which means every 1 becomes a 0 and every 0 becomes a 1. So this is a 0, this is a 1, this is a 0, this is a 0, this is a 1, this is a 1, this is a 0, this is a 0, and now I have this guy is complete. Different color. And so now I have, so I have my 2 statements. My truth table is now complete. The only thing left to do just make this thing look a little prettier by affecting the formatting of the cells here. And there we go. Oops. Oh, it didn't, whatever, it doesn't much matter. But now you can see, well, we compare them and what do you get? You see, for these 3, for every input, they're equivalent, right? This statement and this statement always give me the same result. Zeros are zeros and 1s are 1s across all 8 possible ways to do things. And so this is what we call DeMorgan's law. And it's just part of the logical conclusions that you can draw. And DeMorgan just happened to be the guy, or right around 18 1800s, early to mid 1800s, was the one who devised this way of, using all this logic in this way. Little did he know that over 100 years later, that all of this would start to become much, much more important, because now there was a electronic computing device that could use his logical schemes here and his proofs, to get computers and to make technology and all that stuff. And if he didn't discover it, someone else would have, basically in the 1930s or 1920s or 1940s. Okay, so DeMorgan's law explains this. And so what does it mean? So what you do is, like in this statement, without having to do all the work and doing all the logic tables to figure out what do I have to do, so what you can take is take your statement here, C or A and not B, and what you do is you just work yourself down the line and you take every variable and you negate it. So in this case, C, negative C, A, negative A, negative B, B. So whatever you see here, you negate it, and then basically you just flip the signs. Every or becomes an and every and becomes an or. And so in this case, this or becomes an and this and becomes an or. And what happens when you do things that way, you flip because I've done that, I've flipped everything negative. Notice that when I did this, if you take into account and get rid of this negative sign over here, what these two statements do, what I just explained, is I get to this one here. I'm comparing this guy with this guy, and you can see that they're complete opposites in all 8 possible ways. So DeMorgan's law is a way of flipping the signs on things to basically turn a positive statement into a negative statement, a true statement into a false statement. And so basically that's DeMorgan's law. And then if I just apply and put the negative sign back, that's how I get these two are equivalent logical statements. And just to explain, like, how does this comes naturally from just true mathematics. And let me see if I can make this a little, let me just see if I can do this. So if I had something like, if I had some, I'll fix this up in a second here. And I go, oops, 4 minus 9. Here, give me half a second here to fix the formatting on that. Always how it goes, right? Here, let's see, merge cells, font. Hold on, I want to center, and all the stupid stuff here. So 4 plus, just got to change the font, make it bigger. Okay, so if I have 4 minus 9, what does that get me? The answer to that is -5, of course, right? And so what happens if I want to make this -5 into a +5? Well, I do the same thing I just described. Let me just, oh shoot, I should copy this and put this here one more time. Okay. So what you do is all the positives turn negative, and all the negatives turn positive. And what do I have here? Now compare the two, right? 4 minus 9 is -5. -4 plus 9 is +5. So applying the same rules of flipping the signs of the variables and then flipping negatives into positives or ands into ors get me to the exact same place. And just like I did, if I slap a negative in front of it now, oops, if I slap, let me make sure, slap a negative in front of, well, anyway, you get the point that they are equivalent statements now. God bless it, come on. Everyone wants to see this. So -4, +4 becomes -4, minus sign becomes plus, 9 becomes, minus 9 becomes +9. And then you slap a negative in front, and you end up with the same values. -5 equals -5. So the distributive rule applies here. And so that's what this is, just distributive rules with logical symbols rather than mathematical symbols. So this should cover everything you need to do to get your homework and figure out truth tables. This is one of those things you kind of learn. I learned it way back in the day. They taught us this in, I think, 7th grade. And I'm like, when am I ever going to use this? Little did I know, become part of my whole life. But you get the point here. So if you have any questions about this, You know, this is going to be on our exam. This is going to be, you know, you're going to need to do these kind of things in real life with, it's not just going to be C and A and B. It's going to be, you know, if X is greater than 0, and then if Y is less than 2. And you're going to have, there are going to be times where you have complicated logical statements. You're like, well, there's got to be a way I can simplify this or change this around a little bit so I'm not just writing all these random symbols on there. And that's what the truth table is for, to help you figure out how to simplify your logic. Because if I was given this statement, I'd be like, oh my God, that's crazy. Is there a way I can turn it into something simpler so that, you know, so it's more readable and I guess it's more efficient for the computer as well? And if you're writing in an assembly, I would much rather write this than I would ever want to write that. So thanks for sticking it out with me as always. If you have any questions, if I misspoke, you have any concerns, you can always comment below, or you can email me at swardb@cod.edu. So let's see, this is about the last thing we do in this course prior to moving on over into actual x86 assembly language. I'm excited for that because we can finally throw the math and logic to the side, at least direct. All the weeks we've been spending directly working with logic and math and floating point numbers and integers and whatnot, and we can start focusing more on move statements and adds and copies and all sorts of stuff. So have a great day, everybody. Thanks for sticking it out with me. I'll see you next time in the next